on smooth games optimization and machine learning. It's quite a pleasure for us to host you here. So the history of this workshop is because there has been a lot of interest in two-player games, continuous games, like for generative adversarial network, which have a very different it's very different to optimize these games than to standard minimization. And so we thought it would be very useful for the community in machine learning to actually also make links with the game theory community as well as the mathematical programming community. Okay, so this workshop is co-organized by Gauthier Guidel, who's going to come talk to us a bit more about games, by Yanis Mitkiakis, who's over there in the back, and Vasilis Sirgadis, and me, Simon Lacoste-Julien. All right, so the format is very simple, so we'll start with just some quick opening remarks. Gauthier will tell us a bit more the setup for games so that we're all on the same page. I'll mention a bit of logistics, and then we'll have our first invited talk. So, Gauthier.
Thank you, Simon. So welcome to the Smooth Game Optimization and Machine Learning Workshop. And so as Simon said, it's going to be a quick introduction, and I'm going to try to present a different perspective on smooth game optimization. So first of all, what is smooth game optimization? So here in this workshop, we're going to get interested into smooth and differentiable function because we want to perform first order optimization. Because in most of machine learning application, we cannot afford to use second order information. So we're going to focus on like function where we can compute the gradients and use the gradient in order to perform optimization. And so the goal of this workshop is going to be to understand to what extent single objective optimization in the context of machine learning is different from game optimization. Okay. From a mathematical perspective, like a game, multiplayer game can be formulated as multi-objective minimization, and whereas like standard optimization just require one objective. Okay. So in the two-player games, we have two objectives, like L theta and L phi, and like two players. Where each player controls one different set of parameters. There is the player which controls the parameter theta and the player which controls the parameter phi. And the goal of the game is to find a Nash equilibrium. A Nash equilibrium is a point where actually no player can unilaterally improve its cost function. It's an equilibrium of the game in the sense that if like sequentially the players choose the best action for them in order to minimize this cost function, this point is actually a stationary point. Okay. And so the game is called zero-sum game in the case of like one cost function is equal to minus the other one. And in that case, this two-player game can be reformulated as a min-max problem. And if we can switch the min and the max, for instance, when the cost function L is convex in theta and concave in phi, it's also called a saddle point. Okay, and so what's really important with this denomination is like to keep in mind that here in like min-max problem, we actually want to converge to the saddle point. We don't want to avoid them. For instance, in single objective minimization, when the functions are non-convex, we actually want to avoid saddle point in order to converge to the minima. Here we want to converge to the min-max, which is called the saddle point. So like we just have to keep in mind that like here, saddle points are the points of interest. Okay, and so why this workshop? Because there is lots of motivating application, as Simon said, in machine learning. And one of the most fashionable one nowadays is the generative adversarial network. And why an optimization workshop? Because actually generative adversarial networks are notoriously hard to train. And maybe it's an optimization issue. So like getting more interested in the properties of like optimization of games, and more especially non-convex game, is really important. And there is also like some RL models that can be formulated as min-max, such as actor critic or robust learning policies. Okay, so like in order to be on the same page, what are like generative adversarial networks? So generative adversarial networks can be formulated as a game between two players. The first player is called there's no battery more on this. The first player is called the generator, and the goal of the generator is to generate like image-like data from noise. And the goal of the discriminator is to be able to classify an image, given image, as fake or real. So, like, given an image coming from the generator or coming from a true data set, the discriminator doesn't know from where it comes, and it has to classify it as real or fake. Okay, and so this can be mathematically formulated as two-player games, where the loss of the discriminator is actually like the goal of the discriminator is to maximize the log probability of the well-classified data, whereas the loss of the goal of the generator is to maximize the log probability of the badly classified generated data. So either like just the generated data here, or here like just like minus the loss of the discriminator. Okay, and so why an optimization workshop? Because we think that there is lots of knowledge from game community and like mathematical programming community that could be transferred to this like setting of smooth game optimization. And this would be a way to bring community together in order to tackle the standard issue that appears in such training. Okay, so one also other point is like since we are bringing lots of community together, we want to be clear on the different perspective that exist on games. So like the standard one is basically the multi-objective minimization one that I presented before, where we are looking for a Nash equilibrium, meaning a point where no player can unilaterally improve its cost function. But if we look at this optimality condition, we can also derive the necessary stationary condition from this optimality condition. And so basically the stationary condition are saying that like from the Nash equilibrium, there is no descent direction. So like theta minus theta star are like the available feasible direction. And basically like the inner product with the gradient is always positive, meaning that like there is no feasible direction. And if we merge these two conditions as a big one, like putting these two gradients into a big, larger vector, called F, we get a variational inequality problem. So it means that like actually two-player games imply an associated variational inequality problem. Okay, and so in this workshop, I think it's important to keep in mind that like if we have some work provided on min-max problem, for instance, it can be applied to variational inequality problem. It can be generalized to variational inequality problems, and if there is some results valid on variational inequalities, it can be also applied to games. Okay, and so as a teaser, just before like leaving letting Simon talk again about the logistic, I'm gonna present you some fascinating properties of games. The first one, which is like a bit surprising, is that if we extend naturally like gradient descent and mirror descent from like the single objective minimization setting, actually like this method are not anymore descent method. And like this is really important because in lots of standard proof in single objective minimization, we use this descent property in order to prove, for instance, convergence in the non-convex case or some other thing like that. And so this is not anymore true in multiplayer games. Like even more surprising is that actually some stable stationary point of the gradient dynamics may not be local Nash equilibria. So it's really surprising because local Nash equilibria are the like generalization of local minima, and in single objective minimization, the local minimas are the only stable stationary points. And actually, there may be no stable stationary point. In non-convex single objective minimization, if the function is lower bounded, we know that some minima exist, but actually it's harder to get the existence of stable stationary point in general games. But actually, at the end of the day, from a learning perspective, are we really looking for a Nash equilibrium, or are we just looking for stationary point? This is a good question to keep in mind, and I think there is no clear answer right now. So thank you, and let's continue with some logistic, and then it's going to be Kostis' talk.
All right, thanks, Gauthier. All right, so the schedule for the day. So we have four invited talks and 4 contributed talks in addition to Spotlight. So we'll start with a talk by Kostis, and then we'll have our Spotlight session, 5 Spotlight sessions, 5 minutes each, and then we'll have a poster session. So soon the volunteers should get back with tape, or not tape actually, or sticky points. We have it? Okay, so we have sticky.
In the back of the room, there's a little Ziploc bag with.
Okay, so in the back of the room, there's a little Ziploc bag of sticky putty, and you have to use 1 bar per poster. That's the indication of the workshop. So you can put them anywhere on the walls. Perhaps we can do that at the beginning of the poster session, and then we have half an hour for the poster session. Then there's a coffee break. Feel free to keep doing the poster session or go to your coffee break. And then we have, again, another invited talk, 2 contributed talks, and then we break for the lunch break. Feel free, again, to do more posters. In the afternoon, we actually come back at 2 p.m., so we have about an hour and 40 minutes for lunch. And then we'll have, again, invited talk, contributed talk, break. Feel free, again, to use posters. And then we have actually a panel at 5 p.m. with our invited speakers, and you're encouraged to ask questions as well. So we have actually 1 mic in the front. So when we, and by the way, this is supposed also to be an interactive workshop. So feel free to interrupt the speaker at any point by asking a question. I would ask the speaker to repeat the question because this is actually recorded. And we want to put the talks on our website just after the workshop so that everybody can benefit from what we discussed today. And then we'll conclude and have the poster session. So the workshop ends around 6:30 p.m. Okay. Finally, I would like to thank our sponsor. So actually, we had a generous donation from IVADO, Institut de Valorisation des Données, for recording the talks. And I highly recommend you also to look into IVADO if you're interested in this topic, because it's actually an institute which was created in a donation to University of Montreal to do both machine learning and optimization. And so there's a rich community in open source research in Montreal, and these topics are quite relevant to the IVADO community. And also I thank Mila for the admin support. So Mila is a new nonprofit institute that you might have heard about in Montreal. And so, yes. And on this, I'll conclude and have a nice workshop all. And I'll let Yenis present our first invited speaker.
Good morning. Our first speaker is Kostis Daskalakis. He's a professor at MIT and notable Greek. One could say that he's the most famous computer scientist from Greece right now, definitely. He works on computation theory and its interface with game theory, economics, statistics, probability theory, and machine learning. He has received too many awards to mention, but the most notable one and most recent one is the Nevanlina Prize, awarded by the International Congress of Mathematics once every 4 years, along with the Fields Medal, the true distinction for a computer scientist. And today, he's going to talk about improving generative adversarial networks using game theory and statistics. So let's welcome Kostis. Oops.
Okay. Okay, good morning, everybody. I'm going to talk about GANs and how to use game theory and statistics ideas to, you know, try to attack some challenges that exist in their training. And I'd like to thank the organizers. So, you know, so the goal of this workshop is min-max optimization. I think it's a very timely question. It's a very important problem. It goes back to, has a very rich history in mathematics, optimization, and game theory. Where, as you know, the best case scenario for this problem is when the function f that you're trying to min-max is convex in the parameter of the minimizing player and concave in the parameter of the maximizing player. But which recently has been used in applications such as GANs and adversarial training for finding for you know, protecting classifiers from adversarial examples, where you know this inner function f has no such property, and that exacerbates the importance of understanding the problem in a non-convex concave setting. And also understand the behavior of first-order methods, because first-order methods in this in a high-dimensional setting are the only option. So here's my personal perspective, and with that I'm going to start my talk. So as the applications, as ML develops more and more complex models, I think min-max optimization is going to become more and more important, because it seems natural when you have little idea of what your system is doing. It makes sense to introduce a soup player to keep your inf player honest. So as we develop more and more complex things, we would have to develop other more complex things to check properties of the complex things we develop. Okay, and that certainly happens in GANs. Okay, so in GANs, you're trying to really develop a generator that takes some simple randomness, say Gaussian isotropic randomness, and converts that randomness by passing it through a deep neural net into interesting randomness. So, for example, natural-looking images. But this guy is not going to do a good job unless you force him to produce good images. And for that reason, you introduce another guy, the discriminator, who is looking at images produced by the generator and also images that are real from a database of real images. And it's actually discriminating between the two types of images. And by having this other player, you're forcing this guy to do a good job. So ultimately, this gives rise to a min-max problem, where one player is tuning the parameters of the generator, another player is tuning the parameters of the discriminator. The discriminator is trying to do a good job at distinguishing between hallucinated and real images, but at the same time the generator is trying to fool the discriminator. So this is the game that is being played, and the hope is that at the equilibrium of this game, the generator is producing good images. So, well, of course, there are different types of functions you can plug in to make this reasonable objective. An interesting one that is being pursued in Wasserstein GANs by Archowski et al. Is to basically have the discriminator just comparing two expectations. So the discriminator runs a test on real images and compares that to hallucinated images. And this difference between these two expectations is how well the discriminator is distinguishing between the two distributions. Now, if D was super powerful, if D could implement all possible Lipschitz functions, then at the min-max solution of this problem, the real one, the true min-max, the generator would be minimizing the Wasserstein distance between the two distributions. but more generally, depending on what class of functions you can implement with the architecture of the discriminator, you can get different types of distances between distributions. Now, the parameter vectors of the generator and the discriminator are generally very high dimensional, and that basically, and for this reason, the only real option is to run first order methods, have the two players run first order methods to optimize their parameters. So you typically have them run some variant of gradient descent, which then brings about two challenges. One has to do with training. So it's very common, and I'm going to show you some pictures in a little bit. It's very common that there is cycling in the training of generators. And also, ultimately, the goal of the generator is to produce a high-dimensional distribution that is close to a target high-dimensional distribution. And because the training is not going to work out, to optimality, there are then no guarantees about the quality of the distributions that are produced by the generator. So if you want to, so currently the state of the art is we see very nice looking images. However, to make formal guarantees about the quality of those generators, one has to fix the training, but also develop the right statistical tools to ease the complexity of the problem that the discriminator is facing, and ease the complexity of the computational problem that is faced by the two players in this game. Okay, and the goal of this talk is to try to present some ideas about how you could possibly address these challenges. So I want to talk about the talk has two parts. The first part talks about min-max optimization in general. It does not have to do with GANs necessarily. And the second part of the talk has to do with how to address statistical challenges, more specifically in the context of generative adversarial networks. So let me get into the training challenges. So as I said earlier, when you run first-order methods to solve a min-max problem, you commonly get cycling. And here are some examples of how cycling occurs. So in this first example, the true distribution, so I'm training a GAN, where the true samples come from a mixture of Gaussians arranged, whose centers are arranged on a cycle. And at this bottom panel, I'm showing you the distribution that the generator outputs in different steps of training. And as you observe, in this situation, what happens is that the generator is picking different modes of the mixture and generating samples singularly from that mode instead of producing samples from the mixture. So you get this type of mode collapse, but ultimately this mode collapse happens because the discriminator is hunting the generator who's switching to a different mode, doing a good job for a while, then the discriminator catches up with him, and so on and so forth, and this cycling keeps going. Here's an example with the MNIST dataset, where again, at different steps of training, the generator is producing symbols from a single mode that is not even one of these digits, but some type of proto-digits that the generator decides to focus his attention on. So all these are sort of like more complex distributions, but in this example, I'm going to actually show you what happens in a very simple case. So imagine that the real data are actually coming from a Gaussian distribution that is centered at this vector and has isotropic covariance. And what I'm going to do is I'm going to try to train a generator and a discriminator with the following architectures. I'm going to take a very simple generator that takes as input zero mean isotropic noise and adds that to its own internal parameters, so it's a linear function. The discriminator is just doing linear projection, so it takes a image that's two-dimensional, projects it on its own vector W, and that's his function. So now if you write down the Wasserstein-Gahn objective, so you have a min-max problem over the vectors of the generator and the discriminator of this comparison of expectations. So real samples into the discriminator versus hallucinated samples into the discriminator, which if I basically plug in the expectation boils down to this objective function. Now what's interesting about this objective function is that it's actually convex concave. It's linear in both parameters, in both vectors. So that's a very nice case, as I said earlier, of min-max optimization. This is the best case scenario. You have a convex concave objective. I mean, it's not strongly convex concave, but it is convex concave. And let's see what happens if I try to train to solve this problem with gradient methods. So let's suppose that I have the min player run gradient descent and the max player run gradient ascent in tandem at the same time. So in this picture, I'm showing you what the two guys compute. I'm not sure if you can see the colors. There are two colors, a blue and a orange. And this is what the two curves represent the two parameters. This is a two-dimensional vector for the generator. So these are the two coordinates of that vector, how they change across training. And again, these are the two parameters of the discriminator and how they change across training. Now, for this min-max problem, the optimum, there's a unique min-max optimum, so which is to set theta equal to this vector and set W to the 0 vector. If you violate any of these two conditions, the other player will actually punish you hard. So the only solution is, this guy sets it to 3 and 4, and this to 0, 0. Now, if you see the averages of these curves, they actually are doing the right thing. So the average of these two curves is actually 0, 0. Both of them have average 0 across time. And also this guy has average, the blue curve has average 3, the yellow one has average 4. However, there's no point at which they converge to those solutions. Now you may say, okay, let me try some other type of gradient method. Maybe I'm gonna add, some penalty. Question, yeah.
Why don't you just predict with the averages?
Yeah, so that's a great question. You could.
Please repeat.
Oh yeah, sorry. So the question is, why don't you just output the average? You can, telescoping to what I'm really interested in. When you're training GANs that involve high-dimensional parameters, you cannot take the average you cannot maintain or take the average of the generators that you have encountered in your history. Okay, so our ultimate goal is to do that. So then averaging is not something I would like to do. Question. Yeah, so you're asking what happens if you do stochastic gradient descent. Yeah, so none of these are going to help you. Let me show you what I tried. And this is from a paper. Oh yeah, sorry. The question was, I didn't repeat it?
No, I just wanted
okay.
It was because you said something like you say in high dimension you cannot keep all the counters in the past to average, but you can do the average online, so there's no problem. You can still do that.
You could do the averaging online. Yes, that's right. But again, telescoping to my application in GANs, how it's unclear whether that would work. So I would like point-wise convergence ideally. So here, what did I do? So I tried gradient descent with penalty gradient. I tried gradient descent with momentum. Both momentum and gradient penalty. And then on the right-hand side, I tried, this is a very common practice. Because of the instability of the dynamics, people usually, for every step of the outer player, they run several steps of the inner player. So that, as you can see, so here it's like 1 versus 15 steps. That decreases the magnitude of the oscillations, but still it does not remove the oscillations. Again, the averages are all fine, but you get this oscillating behavior. Now, where do these oscillations come from? So the online learning perspective is, let's go back to the very simple case that actually I was applying in the previous, in the last example that I gave, the bilinear objective. But more generally, the best case scenario, as I said earlier, is when f, the function that I'm min-maxing, is convex in the x and concave in the y. In that case, of course, von Neumann's result applies. That tells me that min-max equals max-min. There is a unique min-max solution, and it's solvable centrally using convex programming. Now, we also have a ton of algorithms that are distributed. So we have a lot of procedures that can be used by the min and the max player of this problem in a distributed way to solve this problem. And in particular, some famous ones are shown here on the slide. Follow the regularized leader, follow the perturbed leader, multiplicative weights update, and so on and so forth. In fact, there is a very tight connection between these methods and gradient descent. In particular, if you take the follow the regularized leader and add L2 squared regularization, you actually recover exactly online gradient descent. So there's a tight connection between online learning and gradient methods. Which is well known. So basically what online learning theory is providing us is convergence in the following sense. You get that the sequence of the orbit of the trajectory that is visited by the players as they're running their no-regret learning procedures, you get that the average converges to a min-max solution. But you don't get that it point-wise converges to the min-max solution, which, as you also experienced in the examples that I gave you earlier, okay? So the question is, can we show point-wise convergence of these no-regret learning methods? And an interesting paper on that topic by Mertikopoulos, Papademitri, and Piliras says that you cannot do that for a large class of FTRL algorithms. Well, that's an interesting result. So what I would like to study in this talk is a variant of gradient descent with negative momentum. So I would like to, in particular, to study these dynamics here, where at every time step, you do, you do a gradient step as you would normally. However, you actually add a little bit of yesterday's gradient. Okay, so you undo today some of the push that you experienced yesterday from yesterday's gradient. Now, where did this dynamic come from? There are many interpretations of what's going on here, but one of them comes from a variant of follow the regularized leader that's called optimistic follow the regularized leader, where basically I am upweighting so FTRL, follow the regularized leader, plays a best response to the history of strategies of the other player with some regularization. Optimistic FTRL upweights the immediately last action of my opponent, thinking that because my opponent is going to be using a smooth dynamic, it's more relevant, that immediately last strategy of my opponent is more relevant for the immediate future. So you can derive this dynamic by what happens if you run FTRL with optimistic FTRL with L2 squared regularization. Another way to derive this is to look at the extra gradient method. Okay, so both of these basically amount to doing this dynamic. Now, does this dynamic help, and why would it? Dimitri. In the linear objective, well, it does something. Let's go to the next slide and see what it's trying to do. So here's a linear case, okay? So it's this is a simple example. So scalar x, scalar y. I'm taking the product of x and y, center that I have. This min-max problem is convex concave. It has a unique solution. It's the 0.5, 0.5 point. This is here. Now, what I'm showing in this picture is what happens if I run standard gradient descent starting from this point. And what I'm doing is I'm spiraling out of the equilibrium. That's what happens, okay? As the step size goes to 0, I convert to a cycle around the equilibrium, right? So if eta goes to 0, I ultimately will convert to a cycle around the equilibrium. Now, why would negative momentum be good for me? Well, let's zoom in into this picture. Let's go to the first step, right? So what's happening is that if I run gradient descent, as this picture implies, I have this spiraling out behavior, which means basically that intuitively I have bad momentum in my dynamics. So if I were to follow the dynamics, I'm kind of like pushed outwards. And what makes sense to do is to actually correct this bad momentum. How? Maybe by taking the gradient in the previous step and adding the negative of that into my dynamics. And what you would hope that happens is that this would actually push you to spiral into the equilibrium. This is the intuition why that should help. Right. So the question is, So the question is, this starts looking like a second-order method. Yeah. So there is a difference of gradients here. So looks like it, except like the way the etas are set up is not quite. But yeah, there is a difference. Like you can take eta over 2 from here and have a difference between derivatives. But if you divide through by eta, you know that difference is not divided by eta. So it's sort of, but not exactly. Question. Right. So the Y player is trying to maximize. So he wants to do ascent. So the question. Sorry, the question was, why are you not taking an ascent step on Y? Yeah. Well, I guess, so the question is, why don't I do gradient descent jointly on X and Y? But one player wants to maximize and the other wants to minimize. So, yeah, so I care right. So I care about, first of all, I want to find a min-max ideally, not a stationary point. I want to find a saddle point. But I don't understand actually how to run jointly gradient descent.
So this would just go through minus infinity. It's an unconstrained optimization problem. So if we go to you could escape.
Question back there? Are you good? Okay. So this is why you would think negative momentum is good for you, right? So you're trying to correct this outward spiraling behavior of the dynamics. And some formal theorems around that are as follows. So I'm going to call this, optimistic gradient descent ascent dynamic, or with negative momentum, I'm going to call it OGDA, optimistic gradient descent ascent. So in a paper last year, we showed that this method exhibits last iterate convergence for this very simple case, really simple case. So unconstrained optimization of a bilinear function. And in fact, the convergence rate is geometric so it goes exponentially fast, if A is well conditioned. So in particular, if I apply this method to my previous example with the Gaussian, the very simple GAN setting, you get this nice, behavior where the dynamics converge to the solution, that's the intended solution. Questions?
What happens if you add noise
Instead
of these positive and negative gradient pieces? Just add noise.
So the question is, what happens if I add noise? You mean remove the gradient, remove this, and not just add noise? You had the same question. Yeah. I guess, if the noise is biasing you, is pushing unbiased noise, I'm not sure. That's right, yeah. So it looks like unbiased noise is not going to help you for the reason that you have the wrong momentum, but I don't know about some other type of noise, yeah. And then another result we have is that if you solve the constrained min-max problem, which is basically all of linear programming, you also have the right variant of this, which is projected optimistic gradient descent, will get you to the min-max solution. So all of linear programming you can solve with this method. and negative momentum is actually important. Question. Left? Okay.
Yeah, so you mentioned the extra gradient algorithm.
Yeah.
It's similar. So you already had the extra gradient algorithm, which converged totally fine for a beginner game, less iterate. So what's the difference here?
I don't know. I mean, so oops. I didn't, for example, I didn't know, for example, about this, like if this was known for extra gradient. Right, so in fact, I learned about extra gradient from Gautier. Right. So now, and that's the most important question, what happens if I go outside of the convex concave setting? So the first thing to note, like if F is not convex concave, the first thing to note is that there is no hope that the stable points of optimistic gradient descent ascent or even gradient descent ascent are only the local min-max points of the function. And here's a nice example, a very simple example, scalar x, scalar y. This is not convex concave. And here I'm showing you the field of gradient descent ascent dynamics. And I'm not sure you can see what's happening in the picture, but the solution, 0, 0 is actually a stable point of the gradient descent ascent dynamics. However, it's not a local minimax point, because if you set y to 0, x is facing this function, and he can certainly decrease it by moving away from 0. But as soon as he leaves, that gives incentive to y to push him to the diagonal, and then both of them want to go back up to 0. So you get these stable points that are actually not locally minimax. So what you can show is that the local min-max points are a subset of the stable points of gradient descent ascent, and this could be strict. And these are a subset of the stable points of optimistic, and this can also be strict. And Adolf et al. Also showed that this inclusion could be strict. Now, the big problem in my mind in this area, okay, and we have only scratched the surface here, is to identify any first-order method that converges to locally minimax or even stable points in general functions fxy. So that's a very interesting open question. Okay, so you want any first-order method that is stable. Okay, that's really cool. So while this is pending, what we tried in this iClear paper of mine that I mentioned, where we showed the convergence in the unconstrained case, we proposed to, we tried all sorts of variants of this negative momentum idea, and in particular, we looked at the optimistic variant, so the negative momentum variant of the Adam algorithm, which is a well-used algorithm for GAN training and optimization in general, even though it doesn't always converge, as was shown recently. So what happens if you try the optimistic variant of that? Just add negative momentum. So we compared optimistic, this version Adam, with Adam in training CFAR, the CFAR data set. And it's a bit of a mess here on the picture, but so here are the error bars. So I'm showing you what happens in the first few epochs of training in terms of inception score when you train on the CFAR dataset using the same parameters that were suggested for Adam by Gulorjani et al. So an interesting thing to point out about this plot is that usually when people run Adam for training GANs, as I said, they do several steps of the inner player for every one step of the outer player. So we run optimistic Adam with 1 versus 1 steps as predicted by the theory. Okay, so the theory says 1 versus 1 should be good. This is what we're running here. and we're comparing to 1 versus many for Adam, and we get this at the advantage. This is sort of like extrapolating from theory that negative momentum would be a good idea, and trying it in practice and getting some advantages. So in general, I expect that negative momentum is a good idea. So I don't have in several cases where I've tried it, it actually improves the stability properties, and I encourage you to use it or try to establish theoretical properties for the method in the non-convex concave setting. Right. So and that's sort of like the summary of this this part of the talk is that negative momentum is a good modification for gradient descent. We have some theory on the convex concave setting. We have some understanding of the stability in the non-convex concave setting, but ultimately, from a theoretical standpoint, it would be nice to have a method that is guaranteed to be stable in that setting. So for the second part of my talk, I wanted to move more to the statistical side and talk about another very important problem that this literature is facing, which has to do with statistics. And back to this picture, let me remind you that what the soup player was trying to do, the soup player was trying to solve a statistical estimation problem. He was trying to estimate the distance between the generated distribution and the real distribution, whereby the distance was defined in the with respect to the test functions that can be implemented in the architecture of the discriminator. Now, the samples that I'm trying to generate are high dimensional, and so first of all, because training is going to be suboptimal, it's not going to get to the right point. There are no guarantees when I finish training my gun. There's no guarantee that I've minimized that distance. Okay, so in the absence of this type of guarantees, the statistical challenges that arise are the following: if I give you a trained gun, can you evaluate the quality of the gun? Can you compare the distance of the generated distribution from the true distribution? That's one challenge. Now, given that the inner discrimination problem is a comparison between two high-dimensional distribution, it's also very important to try to alleviate the statistical complexity of that comparison. And ultimately, if you want to telescope to the future and think about future applications of GANs, you would like to scale up the dimensionality of the distributions that can be generated by GANs. And again, you're going to hit a high-dimensional wall, for addressing any of these questions. So let me be more precise. So suppose I give you a trained GAN, and I ask you to compare the real and the generated distributions. So the fundamental challenge you are experiencing is that the curse of dimensionality, which gives you very simple statistical complexity lower bounds, such as the following. So if I give you sample access to one distribution, for example, distribution of real images, and I give you, white box access, the distribution, and in fact, I'm going to pick Q to be the uniform distribution over the hypercube, then estimating, various distances, for example, the Varsasen distance between the two distributions will require exponentially many samples in that dimension. Okay, so in particular, for the types of dimensions we're looking at, this is a huge statistical barrier. This is a problem that you cannot solve with the images that are in the CIFAR dataset. So the problem is basically infeasible from the start unless you exploit some structure in the distributions you're dealing with. Okay, so this theorem says it's a no-go. You shouldn't even try to do this. Okay. Similarly, given this barrier, you like to alleviate both the computational and the statistical burden that the discriminator who's trying to discriminate two high-dimensional distributions is facing. And again, that's also infeasible unless you use some structure in the real and the generated distribution. Lastly, if you want to scale up, if you're an optimist and believing that current GANs are great and they generate nice faces of people, telescoping to the future, you'd like to generate more complex distribution, for example, videos over several frames. Again, you will face the curse of dimensionality at some point. And again, there's no way to address it unless you use some structural information about the distributions. So what I want you to talk about a little bit for the next 5 minutes, in the last 5 minutes, is how to do that. So what type of low-dimensional structure you could possibly use to actually address this challenge. And the type of low-dimensional structure I'd like to talk about is Bayesian networks. Okay, so Bayesian networks, I hope you're familiar with, they basically describe distributions that have a particular type of factorization. In particular, they describe in terms of a directed acyclic graph, in terms of which you can write the factorization of the distribution. So this DAG over here, this directed acyclic graph, tells me that a distribution represented by this graph can be factorized in this way, which is not a way that general distributions can be factorized. Okay, so in particular, a DAG describes a distribution that can be factorized as a product of conditional distributions where you are sampling a variable, conditioning on the values of the parents of that variable in that graph, but not all the variables that you have already sampled. Now, the question I want to ask is, if you know such structure for the distribution that you're generating or the distribution that you want to generate, can you exploit that to ease the complexity of the discrimination problem? So in particular, I'd like to ask the following question. If I have a base net on a particular graph with n nodes and certain in degree, and I want to discriminate that against another base net on the same graph, how hard is this discrimination problem? So I want to compare, are they equal or are they far from each other? So an interesting statement is that, for example, if I take this to be the total variation distance, is that you can answer this question with a sample complexity that is actually linear in the number of nodes, so linear in the dimension, which is exponential in the in degree of your graph. Sigma is the values that every node of your graph can take. N is the number of nodes, so the dimensionality of your distribution. And what this result says is that the real dimensionality of your problem is D, the in degree, and not N, the ambient dimension. So you have n-dimensional distribution, but in terms of discrimination, the real dimensionality is D, not N. Okay? Okay, so these are tight. You can improve this to root n if you make extra assumption, but ultimately what is important here is that the effective dimensionality of your distribution is D. Now, why is the structure of the graph, how is it used for the discrimination problem? Usually what you'd want to prove to actually argue that the graph is important for discrimination is a localization type of statement of the following form. You want to prove something like, if two base nets are far from each other in variation distance or some other distance, then there exists a small set that witnesses that these two are far. So there is a small subset of the dimensions where if you look at the marginals, the distributions are already far there. You cannot sort of be far, but with no small witnesses of being far. This is what you would try to show. And you can show that for a bunch of distances, okay? So these statements I'm showing here basically, basically implement that goal. Because they tell you that, for example, the KL distance between two distributions is upper bounded by the sum of KL distances of marginals on a node and his parents in the graph. Okay, and the same is true for TV and for Hellinger square distance. Now, if I want to use these types of statements for images, I would like to show that as well for Wasserstein distance. I would like to argue that if two base nets have big Wasserstein, then at least one of these marginals also has big Wasserstein. That turns out actually not to be true. So you can have two Markov chains that have a big Wasserstein distance. However, their marginals on a node and his parent are actually far. So that's not true. But under smoothness assumptions that hold for GANs, it actually goes through. So if you have, and what I want to conclude with is showing you how this can be possibly used in an architecture of a GAN. And my application will be trying to do video generation. Okay, so as I said earlier, even if you're an optimist thinking that GANs can generate very nice images, at some point you'd like to generate videos. Okay, so how do you generate videos? Videos have a lot of frames, so the dimensionality you're looking at is multiplied by a factor of t, where t is the number of frames. Now, an architecture that can generate videos is to take some randomness, process it through a deep net to get the first frame, then use that first frame with more randomness to produce the second frame, and so on and so forth, in sort of like a Markov chain type of architecture. If you're more sophisticated, maybe you can have several back arrows, okay, to several frames behind you and in front of you or whatever. But this could be an architecture for video generation. Now, a standard GAN would collect all these frames and treat this as a video sample. And the discriminator's job will be to compare that video to a video from a database of true videos to certify that they're close. And of course, the more frames you have, this discrimination problem is getting harder and harder. So the subadditivity theorem that I talked about earlier tells you that you don't need to compare these high dimensional distributions as a joint distribution over frames, but that it suffices to discriminate pairs of consecutive frames that you have generated. So you can collect this and that frame, compare it against the first two frames of the target distribution, second, third against second and third of the target, and so on and so forth. So it suffices to solve a lot of small discrimination problems, and that suffices to discriminate the joint distributions. Okay? So you look at the oh yeah, sorry. The question is, am I comparing the same frames of the So I'm looking at, so the question is what exactly I'm comparing. So I'm generating, 1,000 videos, and I'm looking at, for all 1,000 videos, the first two frames, and I look at this distribution, this empirical distribution over the first two frames, compare that against the empirical of the first two frames of the target, the empirical of a second and third versus second and third of the target, and so on and so forth. But what's important is that these are very many small discrimination problems of dimensionality 2 times the dimensionality of a frame as opposed to t times the dimensionality of a frame, ultimately giving rise to a game that is multiplayer and has a generator in the center that's generating everything, and many little discriminators who are discriminating small things. Okay, and so we tried this in practice, but I'm not going to show you. We did actually do that. We generated frames, videos of MNIST digits, and that helps. But let me conclude by saying that min-max optimization has found many applications, and I think many more are coming, but it suffers both the training and the statistical aspect of this very interesting concept is suffering because of the non-convexity and the dimensionality of the problem. And we propose negative momentum as a way to reduce the oscillations, and these subadditivity theorems from statistics to ease the dimensionality, the statistical challenges that are faced. Okay? Thank you very much.
All right. Thank you, Kosti. We have time for one question. So who has the best question? You have a question?
So you try that with videos. Do you think you can even apply that for images, since there are spatial correlations instead of like feeding the whole image, going to comparing smaller patches of images, so that you can accelerate and generate super resolution images more easily?
Right. So okay. So I don't need to repeat that, correct? Okay. So we are actually currently trying to, for example, apply these ideas to progressive generation of high resolution images from smaller resolution patches. Okay. Like in a similar way that progressive GAN generates images. So in general, ultimately, the perspective here is that if you can postulate a hierarchical structure that is generating your distribution that has some Markovian, some conditional independencies, you can exploit those conditional independencies to ease the complexity of the statistical problem that you're facing.
All right, let's thank Kostis
thank
one
you.
more time. And now we have our spotlights. We have, so I would like to ask the spotlight presenters to line up here in the order indicated by the schedule. And, right, so we have the slides. And we have 5 minutes. We give 5 minutes for each spotlight, and that will include one question. So the first one is by Ruishan Liu, or Nicolo Fusi and Lester Mikey. Okay. We can move on to the next one then.
So he's not there?
I don't think so.
There's no Rishan Lu? Interesting. Okay. Well, let's thank the speaker again. All right, so next spotlight. Yep.
Chidubem Araji or Bert Huang? Okay.
Are you sure these are not the afternoon spotlights?
Oh,
Oh no.
that could explain.
Sorry about that.
Yeah, that would. Thank you. That would make a lot of sense. Yes, that was the afternoon session. Interesting. Good.
That makes sense. Okay.
Let me just open all of them. You can make a joke in the meantime.
Sounded pretty funny.
All right.
Okay. So now we should have it right. Mingrui Liu. All right.
If you want to use this.
Hi, good morning, everyone. Thanks to the organizer for this workshop. My name is Tianbao Yang. Our work is about provable non-convex min-max optimization. This is a joint work with students Minrui and student Heather and my colleague Chi-Hong Li. So we consider non-convex, non-concave min-max problems, which is also called saddle point problems. So it has broad applications in machine learning, I think everybody knows, generative adversarial networks. It also has application in reinforcement learning and more general adversarial learning, and also robust optimization. But we know that solving general non-convex, non-concave min-max problems is NP hard. What I mean is finding the saddle points. So instead here, we consider a class of non-convex, non-concave min-max problem, which is we call weakly convex and weakly concave. What I mean by that is if I add a quadratic term on x and minus quadratic term on y, it will become convex and concave for some positive real parameter. Okay, so this class is actually general enough to include smooth functions. So if the objective function is smooth, so this is in this class, and also include some non-smooth problems. Okay, so and also we're going to find epsilon stationary solution x, y in the domain capital X and Y such that the distance between 0 and the subgradient of the objective function plus the indicator function of the constraint domain, it is less than epsilon. Okay. And also, in order to handle the non-smoothness of the objective function, we also found nearly stationary points, which is found a point close to a point which is epsilon stationary. Okay, so we proposed the algorithm, which is actually a framework. So it is inspired by the proximal point method. So we run the algorithm in multiple stages, and at each stage we construct a subproblem, which is by adding a quadratic term on x minus quadratic term on y to the objective function. Okay, so by carefully choosing the gamma parameter, which is less than rho inverse, so this subproblem will become strongly convex and strongly concave. And then we'll employ any suitable algorithm for solving strongly convex and strongly concave min-max problem to get a new solution, new point zk plus 1, which will be used as an initial solution, and also use a reference point for constructing the next subproblem. And one point I want to mention here is that for each subproblem, we don't need to solve them exactly. We only need to solve them inexactly with some increasing accuracy. Okay, so this is our conversion results. So we make the following assumptions for the set-valued mapping FZ. Okay, we assume the constraint domain X and Y are compact convex sets, and also there exists a solution Z star to the min-t variational inequality. Okay, so this seems to be the weakest condition we have seen in the literature. And then with the gradient complexity results, so we depend on different algorithms for solving the subproblem. So we can use stochastic subgradient methods without the Lipschitz continuous assumption on FZ. We get 1 over epsilon 6 complexity. If the problem is deterministic, we can also use gradient descent method, extra gradient methods, and Nesterov accelerated methods. Under the Lipschitz condition, we can improve the complexity to be 1 over epsilon square. And also extra gradient, Nesterov extra gradient has the improvement on the dependent on the condition number. And if the problem is finite sum, we can also use variance reduction, accelerated variance reduction, get improved rates. So it looks to me, to our knowledge, these are the first results for finding stationary point for non-convex, non-concave min-max problem. And also, if the problem is concave in terms of y, we can also strengthen our conversion results. So we can find epsilon stationary solution to the equivalent minimization problem, which is distance between 0 and the minimization objective, gradient of the minimization objective is less than epsilon. And also we have the result of stochastic gradient, subgradient method, 1 over epsilon 6, and a family strongly concave problem, we can improve to be 1 over epsilon 4. And using stochastic variance reduction method, we can also improve to be n over epsilon square. Okay, so that's all. Thank you. If you are interested, you can come to our poster later on.
Thank you. We have time for one question. Yes, let me bring in the mic.
How do you define the condition number?
Condition number?
You had a parameter rho there. What does it mean?
Rho is a weakly convex parameter. So if it is convex, if it is smooth, rho is at least less than the smoothness constant L.
Okay, thank you.
Let's thank the speaker again. Pavel Dvoreczynski.
Good morning to everyone. This is joint work with Yuri Nesterov and Vladimir Spokojny. So in this work, we consider zero-sum dynamical games with two competing objects. So we have a linear dynamics for each of our two objects, and also have some some convex concave performance index, which depends on the controls U and V, and also at the position of the objects at the final time moment theta. So then the goal is to find the optimal controls as the functions of time. We define B and C as operators of solution of differential equations. So in that sense, we have this linear constraint that the position at the final moment is a linear function of controls. So then the main idea is to write as a saddle point problem with linear constraints. Adding Lagrange multipliers for linear constraints, we rewrite this problem as a finite dimensional saddle point problem of minimization in lambda and maximization in mu. Then, since we have this finite dimensional problem, we apply some existing methods for finite dimensional variational inequalities. So for example, we can apply Nesterov dual averaging. So, and adding some averaging in the primal space, we can obtain complexity convergence rates for duality gap, 1 over square root of k, and also for linear constraints feasibility. So here is a simple two-dimensional illustration of a dynamical system. So we can find piecewise constant approximations for the controls. We also depict some theoretical and practical convergence rates and see that in practice the convergence rate is the same and proportional 1 to the square root of k. Adding some more assumptions, namely if we assume that our problem is strongly convex concave and we have some Lipschitz conditions for the gradients, we can prove that actually in the corresponding variational inequality, the operator is Lipschitz smooth, and then we can apply a method for smooth variational inequalities, namely dual extrapolation method, and obtain a fast rate 1 over k. So this is a slightly different example with strongly convex concave term. So we also can construct these optimal controls as functions of time. And the same picture, so now we have in practice also faster convergence 1 over k. So that's all in short. For details, please come to the poster.
Thank you. So, questions? All right, let's thank the speaker again. Okay, now we have the same speaker for another spotlight.
So this work is on variational inequalities with Hölder continuous monotone operators. So this is joint work with Alexander Gasnikov, Fedor Stanyakin, and Alexander Titov. So in this work, we consider variational inequalities. So we need to find such z star that it satisfies this inequality for all z from the set, some set q. We assume that the operator is Hölder continuous, so there is some Hölder constant, Hölder parameter nu and Hölder constant L nu. So this is a generalized condition. So for nu equal to 1, we have non-smooth operators with bounded variation, and for nu equals to 1, we have smooth operator. And we also assume that the operator is monotone. So one of the motivation is that saddle point problems can be considered, can be solved using methods for variational inequalities. Another motivation is that if we have some non-smooth problems with non-linear inequality constraints, we can write a saddle point Lagrange problem, and it will have a different level of smoothness for the primal and for the dual problem. So in this sense, how can we solve it? And we want the method to be adaptive to these different levels of smoothness in the primal and dual problem. And there are some existing methods for Hölder continuous fields. Yeah, better? But they require to know parameters nu and L nu. And we want to obtain to the same bounds, but to be adaptive and not require knowledge of these parameters. So we introduce standard proximal setup with prox function and Bregman divergence. So, typical examples are squared Euclidean norm and entropy setup. And then we modify the mirror prox method of Nemirovsky. The main difference here is that we have this line search. So we want to adapt to this Hölder constant. Mk is our approximation for this constant. And the condition which we check on each iteration is as follows. So by using this adaptivity, we can obtain a method which is adaptive to all the constants and has convergence rate which is infimum in terms of nu of so this depends on epsilon, and this corresponds to the estimates given by the Nemirovsky method for with knowing parameters, but in our method we do not need to know them. So we also consider as case corresponding to strongly convex optimization, namely the case of strongly monotone variational variational inequalities with strongly monotone operator. So this is the definition. We now have a kind of quadratic lower bound for this operator. So then we can show how we can restart the method from the which I described before. So we can restart it and obtain optimal convergence rates for this case of strongly monotone operators. So for example, if we have a smooth field, then we can have a linear convergence. So and we so this is a small numerical illustration. We have non-smooth problems with non-smooth inequality constraints, and we empirically have 1 over epsilon dependence. Despite that, the problem is completely non-smooth. So actually, we can solve non-smooth problems with the rate corresponding to smooth problems. Yeah, and these are some extensions. So in the paper, we also have some inexactness in the terms of the vector field, and we are working on generalization for stochastic case and for composite case. Yeah, so for details, please come to the poster.
Thank you. There's a question.
Hi, thank you for the talk. At the beginning, you mentioned that you were solving the weak variational inequality problem. To what extent is it weaker than the normal one? And are they equivalent or not? I guess no.
For the case of continuous monotone operator, they are equivalent. Yeah. So it's more or less a matter of how you write it. So in this, so the strong one will be g of z times z star, 0 of z star times z star minus z less or equal than 0. But if it's monotone and continuous, they are equivalent.
All right, let's thank the speaker one final time.
Thank you.
All right, so this is Panayotis.
All right, thank you for having me. This is joint work with Radu Bot and Phantom Wong from University of Vienna and with Matthias Staudigl from Maastricht. He was supposed to be giving the talk today. Unfortunately, he couldn't make it, so you're stuck with me. And the motivation for this work is, again, variational inequalities, because they actually arise as a very natural framework for the zoo of optimization problems that we encounter in machine learning, coming from stochastic optimization to saddle point problems, and, of course, for this workshop, continuous games or smooth games. And as I said, thanks to the previous two speakers, you've already seen the formulation of a variational inequality. This is the weak or Stampacchia form. And what we are interested in this talk is exactly to develop a method for solving a certain class of these variational inequalities known as pseudo-monotone inequalities. Now, in a general variational inequality, all the previous examples of optimization saddle point problems or Nash equilibrium problems, their solutions are solutions of the variational inequality. The converse does not hold. And one general class under which this holds is the class of pseudo-monotone inequalities in which there is an equivalence of solutions between a variational inequality and the corresponding problem at hand. And if you are interested about what kind of problems you can get in the pseudo-monotone world, you can get functions like sigmoids, which are very crucial for the training of neural nets. All right. So the golden rule for solving this is either gradient descent-ascent, as Kostis said in his talk, or forward-backward method, as is known in the world of operator theory. The problem is, again, as Kostis showed, that these methods do not converge even in the case of, sorry, how do I go back? All right, even the, come on, okay. These methods do not converge even in the case of bilinear problems. This is what happens, they can circle outwards. The addition of an extra forward step or an optimistic step, depending on where you're coming from the world of Korpelevich in the 70s or optimism from Racklinger Stridaran in 2013, this stabilizes the method, but not in the case of stochastic problems where you have noise and which could perturb the method. And what the main takeaway message of our work here is that if you introduce also a variance reduction step, then you can get convergence in pseudo-monotone variational inequality problems with an FBF method at the rate of 1 over n. And if you would like any more details about this, I would be happy to discuss them in the poster. Thank you.
Thank you. All right, we have time for a couple of questions. That's right. All right, let's thank the speaker.
All right, thank you.
Our last spotlight is by Hugo Berard.
Hi everyone. So today we'll be presenting a variational inequality perspective on GANs. So as we've seen, GANs are hard to optimize, and one reason people have given is that sometimes gradient descent doesn't converge, for example, on a bilinear min-max. So it's illustrated on the right here. And so the good news is that actually this has been studied in the optimization literature for quite a long time, especially in the variational inequality literature. And what we propose here is to cast GANs as a variational inequality problem, and this enables us to have standard methods from optimization for GANs and with convergence guarantees for convex and stochastic loss functions. And we also propose a new method called extrapolation from the past that converges on this problem. So let's describe quickly the variational inequality perspective. So usually we can formulate a GAN as a two-player game where we're trying to look for Nash equilibrium. And basically, we can, instead of looking for a Nash equilibrium, what we can do is that we can look for a stationary point, which is a necessary condition for a Nash equilibrium. And this is equivalent under some convexity assumption. And then basically, we get to characterize stationary points. We have those two inequalities, which are the variational inequalities. And basically, what they tell us is that if a point satisfies those inequalities, then there is no feasible descent directions at these points. So I will present now two standard algorithms from this literature. The first one is called averaging. And basically, if omega t is obtained through, for example, a gradient method, then we can just average all the iterates. And this will converge even if gradient descent has some cycling behavior. And this can be efficiently implemented in an online fashion. So we don't need to store all the iterates. We can just compute it on the go. And this can be combined with almost any methods. But one condition is that the iterates of the method have to be bounded in order to converge. So this is not always the case. There is more details in the paper, and we can talk about it in the poster. The second method I'm going to talk about is extra gradient. And so the intuition behind extra gradient is that we want each player to look one step into the future and try to predict the next move of the adversary. So basically what happens is that if we are at omega t, then we can compute the gradient at this point, and we can apply it to get a new point that we're going to call the extrapolation point. And then you can compute the gradient at this point. And instead of applying at this point, we can apply it at the previous point to get the new estimate. And this is a standard method in the variational inequality literature. It does not require averaging for non-stochastic cost function. And this is theoretically and empirically faster than averaging. Well, we also proposed a new method because for extra gradients, we need to compute the gradient twice at each iteration. And so instead of that, we propose to reuse the previous gradients. I won't get too much into the details, but we can talk about it at the poster session. So about the experimental results. So here on the bilinear example, we can see in blue that the gradient method doesn't converge, but that all the other methods that we described before actually do converge on this problem. We also try those methods with GANs, like on CIFAR 10. And what we showed is that if we combine extrapolation and averaging with Adam, we're actually able to achieve state-of-the-art results. So here we have extra gradients, what we call extra Adam, with a 8.26 inception score. And we hope that this will. Oh. Okay, we hope that this will that people would get more interested in those topics, and that this will bring better convergence results for GANs, and also that the optimization literature is going to look more into non-convexity and stochasticity in the context of min-max problem and games in general. Thank you.
All right, thank you. Any questions for our speaker? Yes, let me bring you the mic.
Did you take the standard algorithm in this case, or did you also do additional tricks like alternation and so on and so forth?
So no alternation for our methods. We don't need to do alternation.
Okay.
So that enables us to be faster also. So this is like the main advantage is like we're able to get better inception score, and also we're able to converge faster. We don't need to do 5 iterates, for example, or even like it's simultaneous. We can do update both the generator and discriminator at the same time.
Did you try this on other data sets like Alsan or Celeb A?
No, we haven't done like but so we're going to post the code online soon, and so people can play with it.
Thank you.
All right, thank you. So now we have our poster session. So I invite the people who brought posters. We have tags to put them on the walls. I can help you. So, and then at 10:30, there's a coffee break.